Welcome everyone to this video lecture. I'm here with Francesco Ambrogi, Adjunct Assistant Professor at Queen's University in Canada. Welcome, Francesco.
Thank you for asking me here, Gianmarco. It's great to be here.
All right, so Francesco, tell us a little bit about your research during your PhD studies. What aspect of fluid dynamics did you look into?
Absolutely. So I did my PhD at Queen's University under Professor Primelli's supervision. He's very well known for his research on large eddy and direct numerical simulations of turbulent flows, very phenomenal research studies. And my topic was specifically the influence of dynamic or unsteady adverse and favorable pressure gradients on a flat plate turbulent boundary layer. Now, a flat plate turbulent boundary layer might not seem extremely connected to what we are discussing today, but when we think about the shark, let's say surface, the flank, for example, like we see in the picture right here, if you take a subset of that, very big flank, you can assume that it's a flat surface, and on that surface, the shark definitely experiences adverse or dynamic pressure gradients, which greatly impact the dynamic of the flow over them, as we will discuss later. So my specific research area was understanding how this unsteady behavior actually affect the near wall region.
All right, very interesting. And how is this, what's the inspiration behind this research? Why were you looking at unsteady pressure gradients? Why were you looking at, why is this relevant to the shark and to other fields?
So I think the most important aspect is the fact that unsteady pressure gradients are actually extremely common, not only in, for example, aerodynamics, which is the first application one might think of when you are either take off or landing, for example, the airfoil or the surface of your wing is experiencing unsteady pressure gradients, but also turbine blades and rotor blades and swimming animals, for example, like shark, dolphins, and any fish, any, for example, tail beating frequency animal like birds. So it's extremely common, though it's extremely hard to predict and to model. I think that's why with the raising power of computational resources, one is moving towards trying to simulate and maybe uncover details of that particular phenomenon. Up until now, we have a large body of experiments, but the great advantage of numerical simulation is that we can actually get extremely close to the wall. And basically see what's really going on, which I think it's the beauty of it. We can really uncover physical mechanism that can maybe spawn new technologies.
The great advantage of numerical simulations is it provides so much more information about the flow compared to experimental measurements, to field measurements. We have so much more information that we can analyze and study. So yeah, so let's
100%.
dive into more into understanding what's so special about sharks. Why sharks?
Absolutely. So I think, the first thing we have to think about is that sharks have been around on Earth for millions of years. So they have had, huge amount of time to actually develop and evolve. And I think the beauty of it is that they actually don't have on their surface what we might think of fish scales, but they have developed something known as dermal denticles. These actually look very different from fish scales, and we will analyze later why this has an impact on the fluid dynamics over them. I report here one of the most studied sharks on the top right of this slide. You will see the short fin mako or dogfish. This is one of the fastest swimming animal shark on Earth, and it has developed on its surface denticles as small as 200 microns, basically, in dimension. And this shark specifically can maneuver in very extreme circumstances, and I think this is the reason why it is extremely attractive from either an hydrodynamic or an aerodynamic point of view, because if we can learn something from this specific shark, then we can maybe apply it to developing new technology in aerospace or in submarines or sports, and you name it. But I think it's extremely, extremely interesting.
So we are looking at this incredibly fast shark, and we're asking ourselves how can they achieve such high speeds? And in fact, if we look at the bottom right, the image on the bottom right, we can see the denticles, the dermal denticles that you were mentioning. In red, you see one of them highlighted, and you see that they have this very peculiar shape. We will go into the details of how this shape allows faster flow and less drag.
So I think, before we actually dive into the physics and into the details of the shark skin denticle itself, we should first clarify one very important concept, which is, drag reduction and what drag even is. So, drag force, as you might have studied in your course or you might know from previous courses, is basically the force that opposes the motion of any object that moves through a fluid. So if you take an airplane, for example, the airplane, as it cruises in air, is experiencing an opposite force given by its interaction with the air outside. Now, it's important for this presentation to actually divide drag force into two components. There is going to be at any time a skin friction drag, what is commonly known as viscous drag, and this viscous drag is basically dependent on the surface area, on the viscosity of the fluid outside, so basically air, water, and the roughness of the surface, so the surface imperfection.
This skin friction drag is the force exchanged by the fluid, the air or water sliding over the surface and the surface itself. And this is a viscous mechanism.
And then the second component is pressure drag, or what is commonly referred to as form drag. And this is actually generated by the difference in pressure from the front and the rear of the object. The connection to the physics of it is more towards the object shape, the flow speed, and the fluid density. You might think of, for example, a very blunt body disrupt the flow way more than a very slender and streamlined body. Therefore, the form drag of a cube, for example, is way larger than the form drag of a flat plate. Okay, so it has to do with how this object disrupt the flow.
And this is what we see in airfoils, in aircraft, where we see the recirculation at the trailing edge of an airfoil. It's caused by that pressure difference between the suction side and the pressure side. And we see that separation at the trailing edge. That is directly related to this pressure drag. That's where that pressure drag comes from.
Precisely, and I would like to just highlight, as is said in the bottom of this slide, that the viscous drag has more to do with the surface texture, but the form drag has more to do with how the object disrupt the flow around it.
So now that we have discussed a little bit more in detail this important distinction between skin friction drag and pressure drag, let's try and understand, explain to us how is this, what happens in over the denticles that allows a reduction of drag. What kind of drag are we reducing? What's the mechanism of drag reduction in with the denticles over the skin of sharks?
Yeah, absolutely. And the first thing I'm going to do is I'm going to show actually a picture, which you can see in the top left here of the slide, which is a look from above of shark skin, very close up. picture, what you will notice is that basically these denticles, they overlap and they create some sort of like organized lattice, where you have this very organized streamwise ridges and valleys. So in the late 1980s, many researchers started modeling the effect of shark skin really by assuming that shark skin denticles, as you can see in the picture on the top left, they behave like riblets. Um, and they did so by modeling and simulating and experimenting also various type of flows over different geometries, riblet geometry. So we have trapezoidal riblets, blade riblets, scallop riblets, and V-shape. And these researchers have actually found that there is a drag reduction mechanism associated with riblets, and it's actually dependent on the riblet size or the denticle size, as you can see in this plot on the bottom right. So when you reach basically a threshold denticle size, you will appreciate some percentage of drag reduction here in the top right. And I think the most notorious experiment here has been the one carried out by Wen and Lauder in 2014.
And so this drag reduction is very interesting that this was observed because they actually found out what is the cause, the source of this drag reduction. And basically, researchers found out that there are structures of the flow. There are these vortices that are present in the flow and that are strictly connected to the friction drag. And they found out that the riblets raise these vortices. They push them away from the wall. And by doing so, the effect of these vortices of generating friction drag is actually weakened, is reduced. So we achieve with riblets, we achieve a drag reduction by pushing these drag generating vortices away from the wall itself. This was a major discovery in this field, in this aspect. However, this is something that is related to riblets. It's not exactly what's happening with denticles. In fact, Francesco, what are the main the actual differences between riblets and denticles?
Yeah, so we have to actually remember that this is kind of like an idealization of the geometry if we think about the shark skin as riblets, but truly denticles are not riblets. And there are three main basically differences that we can highlight. One is, of course, the denticles are highly three-dimensional, whereas riblets are 2D basically. Riblets have a constant cross-sectional area streamwise. If you take, for example, the cross-sectional area of the scallop riblets streamwise, it never changes, but you can clearly see that along the shark's body, denticles and cross-sectional area actually do change. And finally, another important distinction between riblets and shark skin is that denticles are flexible and they can bristle. And this is something that has been proven kind of recently, actually. And so you can, first of all, observe experimentally that denticles, both in shape and dimension, change along the shark's body, but also they change in their flexibility. And in region, for example, like this, the flank of the shark, we can clearly observe that denticles go in some, based on the configuration of the flow, they go from the resting position, which is aligned and overlapping themselves, to a bristling position, which can also be as much as 50 degrees angle with respect to the flow direction.
And so this is now a very interesting discovery by these researchers because the denticles are breaking down the reverse flow. And by doing so, they are reducing that form drag that we were talking about previously. In fact, if we take a look at this video, we can see that anytime that the flow is moving from left to right, and anytime that there is flow going back to the left, the denticles lift up, they bristle, they raise up to block that reverse flow.
And in fact, actually, flow separation is something that happens very commonly, both in airfoil scenario, on the shark skin surface, and it's basically the strength of this reverse flow that activates this bristling mechanism. And by the denticles bristling up, the size of the separation region can be reduced. And if you reduce the size of the separation region, then you basically have a smaller separation bubble, you have a smaller contribution to the formed drug, and you therefore reduce drug.
And so now let's take a look at how we can use this information that we discovered about sharks and use it into engineering, use it into aeronautics. This is a common practice in the scientific world. We observe nature to learn from it and apply what we learn to aeronautical solutions, to technological solutions. In fact, here are two other examples of how we have used nature observation to create, to improve technological solutions. In fact, on the left side, we see the kingfisher, a bird that inspired the shape of a bullet train to reduce the pressure waves generated by the train. And on the right side, we see on the left, you see a wind turbine with these tubercles that are inspired to the fins of whales. And these as well improve lift production in wind turbines. In a similar way, we use the information, the knowledge that we acquired from sharks to improve aircraft technology and aircraft performance. In particular, in this study that we see here, the researchers designed a very thoughtful experiment to analyze the performance of a wing, of an aircraft wing, with the presence of some type of structure on the wing itself. And they analyzed, as you see from top to bottom on the left side, you see that they analyzed first a line of objects shaped like denticles on the surface of the wing. In a second instance, they analyzed a structure on the wing that it's uniform in the span, but that has the same dimensions of the denticles, to investigate what happens when it's just a bump, a two-dimensional bump that has the same dimension of the denticle. And in a final analysis, in a third experiment, they analyze a surface that it's much more complex, three-dimensional, and that resembles a lot the distribution of denticles on the skin of a shark.
Also, what is important to add about this experiment is that, as you mentioned before, this is like maybe one of the first experiment that went into the details of, what is the influence of shark skin on the flow. But we don't have to forget that actually, when we analyze engineering problem, we break down the complexity of the problem and we analyze then subsequent layer of complexity. So for example, here we started with one line of denticles, but we know, as we saw before in the picture, that actually denticles are way more organized in the streamwise and spanwise direction. And so someone might ask, but how is this study going to be useful to understand the physics of shark skin? But the question should actually be, how can we make it useful in aerodynamic application? So here, I think the purpose of this experiment was actually to prove that maybe for aerodynamic studies or for aerodynamic application, we can actually use denticles to reduce drag.
Yes. And in fact, what they found out in this experiment, as you see on the right side, is that if we look at the ratio of lift to drag versus the angle of attack, in the three configurations that we see on the left, we see that there is always a better ratio of lift to drag, so better performance of the wing in the presence of a three-dimensional shark-inspired profile. And the one thing that's important to point out in this study is that, unfortunately, for practical reasons, the Reynolds number studied was not as large as one finds in realistic aeronautical flows. It's not a final conclusion about the improvement that these geometries can bring. Just to make it a little bit more complicated, because it wasn't complicated enough, manufacturing these structures, these geometries in real life for aircraft is not trivial at all. It's quite challenging because of the shape of the denticles and because of the curvature that they have. It's quite complex to manufacture them in traditional methods. One method that has been successful and that it's being applied today is 3D printing, and specifically because of the size, the very small size of the denticles. What's the size of denticles, Francesco?
200 micrometers in the case of the short fin mako shark.
That's right. So we're talking about really tiny geometries on top of the surface. And the one way that has been found to generate them is with this direct contactless microfabrication that uses UV light to cure the material and create these geometries on top of the surface. And then these surfaces, these films, are applied to the surface of the wing, to the surface of the fuselage of the aircraft. So now, why do we want to do this? Let's go back to the original reason, the motivation of this research. We do this because we are reducing drag. We want to reduce drag, and reducing drag means reducing the amount of energy that we have to spend to fly the aircraft. Energy equals fuel in airline business. So what does it mean economically? What can we save by applying these films of shark skin on the wings of an aircraft? So from the research conducted by Lufthansa Technik, it was found out that the application of this surface, of this shark-inspired surface that Lufthansa calls AeroShark, the savings can be substantial, as you see in the table shown in this slide. And the more important thing is that this is a quite flexible solution. These films can be applied to any aircraft. They can be applied at any point in time, and they have a reasonable durability, which finally brings in economical advantage for the airline and a more sustainable aviation practice.
100%. And as you can see from this slide, actually, the economic savings just by reducing drag by, let's say, 0.8% or 1% are actually extremely high. So they do matter. So I think, this stream of research that companies are actually going into, shark skin application or, texturing is actually quite important.
In fact, that's the final objective: reduce CO2 emissions, reduce expenditures to have more sustainable and more cost-effective solutions. So we've seen today how, starting from the observation of natural phenomena and systems, we can come to technological advancements. And this is something that keeps pushing the limits of technology. We keep moving forward by keeping imitating nature. This is what's really fascinating to me.
Absolutely. And I think, the incredible part is that with the advances of, computer power, artificial intelligence and new ways of carrying out experiments, I think, shark skin has actually not ended playing a role in both aerodynamics, hydrodynamics, and engineering in general. So keep your eyes open, because I think we will have very nice surprises in the future.
Yes, and in fact, if you can think of some natural phenomena that you think could inspire an aviation innovation, let me know. Think about this. Think about something that you think might be the new revolution, the new improvement, the new advancement in aeronautical technology and aeronautical solutions. Francesca, it was awesome to have you, and I think it's really a great honor for us to have you as a host and explain us the dynamics, the physics of this incredible technological innovation that has entered the aviation world.
Thank you, Gianmarco. Thank you for having me here. It was a pleasure. Nice to meet everybody. Maybe I'll come visit sometime. But for now, I think, again, thanks for the opportunity.
That'd be lovely. Bye-bye, Francesco. And bye, everyone.
Bye-bye. Thanks, guys.